right, in this video, we're going to take some partial derivatives of a natural log function. Hopefully make this nice and simple. Someone actually commented on another video I made of a very similar problem saying, hey, there's this easier way. Why don't you do it this way? And I said, yes, yeah, that is way easier. Why was I making it difficult? So let's try to simplify this as much as possible as we go through it. What this simpler way requires is it requires you to understand a few of the basic ideas of, as far as the logarithmic properties that go into this and some exponent rules. But overall, I think way easier than how I was doing it before. Either way, what I would do is I would begin by rewriting that cube root as a 1/3 exponent. Okay, from here, I saw it as, hey, we're going to do the chain rule. We're going to work through it that way. All right, but instead, what I was told was, hey, why don't you just make this as easy as possible? Let's bring that exponent, that 1/3, into each one of these terms, or, each of these variables on the inside. So to bring the 1/3 to the inside here, what we're going to do is we're going to multiply 1/3 by each of the current exponents. So we get x raised to the 1/3 power, multiplied by y raised to the, well, we have 2 times 1/3 makes 2/3 for our new exponent there. All right, from here, what we can do is we have two things multiplied together on the inside of a natural log. So we have a logarithmic property that says you're allowed to go ahead and split this apart into two separate natural logs. Multiplication is going to become addition. So we have natural log of x to the 1/3 plus natural log of y to the 2/3 power. All right, at this point, we can go ahead and we have an exponent attached to everything on the inside of our logarithmic function. So we're allowed by another log property to move these exponents down in front and make them multiples. So in this case, we can say this is the same thing as 1/3 multiplied by natural log of x plus 2/3 comes down in front multiplied by the natural log of y. All right, why we want to get into this and split things apart like this is because we're about to do partial derivatives. In partial derivatives, if we haven't partial with respect to x, we're going to treat x as though it's our only variable in this function. So if you see a y, you treat that as a constant when you're taking the derivative with respect to x. And it's the opposite if we're taking the derivative with respect to y. All right, so the only place I see an x here is this one spot right here. So that means that first term, as we take the derivative, the 1/3 can come along, and then the natural log of x is, its derivative is 1/x. And then you could say, if you wanted to, plus, well, everything in that 2/3 times natural log of y, there aren't any x's involved, so all that's a constant. The derivative of a constant is always going to be 0. All right, simplifying this a little bit, we get 1/3x. Okay, well, that's not too bad. Let's evaluate that partial derivative with respect to x at 3,5. So all we have to do is we have an x value here of 3, a y value of 5, but I don't see any y's involved there, so we can just say 1/3 times 3. We've replaced the x with a 3, which works out to be 1/9. Okay, not too bad. Next, we want to do the partial derivative with respect to y. Well, we only have y this one spot. So this shouldn't be too bad either. That whole first term, the 1/3 times natural log of x, its derivative is simply going to be 0. Because we're treating that as though it's a constant because y is being treated as our variable with this partial derivative, plus 2/3 comes along, multiplied by the natural log of y, its derivative is 1/y. Go ahead and forget about that 0 plus. At the beginning, multiply our numerators, multiply our denominators. We have 2 times 1 makes 2, 3 times y makes 3y. And then evaluate this again at 3,5. That's an x value of 3, a y value of 5. We don't have any x's in this, so we're just going to replace the y with 5. So 2 over 15 after some reducing down, and there's our solution. Hope this helps out. I really suggest getting comfortable with those log properties so you can efficiently split this apart. It makes taking these partial derivatives way, way, way easier than doing the chain rule and that sort of thing. So hope this helps out. Good luck as you're working on partial derivatives.